Today I'm presenting to y'all from the red team about the filter wash pump control system, along with Casey Valans and Chris Hawk. During the presentation, they'll tell you a little bit about the background information on our flow control system and also briefly talk about the steady state operation just to give you an idea of where our linear operation is. I'll also talk about the transient flow of the system along with the frequency response and the root locus. Casey will talk about the proportional controller modeling along with the experimental data, and Chris Hawk will talk about the proportional integral. First of all, the pump control system is a filter wash media station at a sewage treatment plant right here in Chattanooga. The input is the motor power and a percentage, and then you have your pump system, and the out pump is the flow rate through the pump. The objectives for today are showing the development of the steady state operation curve, also a brief review of the system transfer function, a review of the Bodie plots and results. We'll also tell you about our PCM modeling parameter analysis and give you some results on the PCE result based on the lower, mid, and upper ranges. And we'll also give you some information on the proportional integral design parameters and also tell you about our results for the lower, mid, and upper ranges for both. Here's an example of one of our steady state input and output curves. Our output average is around 23.8 pounds per minute at an input of around 69%. Here's an example of the steady state operating curve. Our operational input range pretty much all the way through our ranges from low to high, and that's from 20 to 38 pounds mass per minute. That just shows that it was pretty much linear all the way through, and you give a certain percentage, and from that curve you can determine what output you'll receive from the input percentage. For the transient flow system, we have simulation inputs. Input baseline is the initial pump power. Input step is the change in pump power. Time of step is time at which the step occurs. And the duration of the experiment is however long the experiment runs before the step and after the step. The output will rise by a certain amount, which is the delta R, and that's your step raise. And the output will lag after input step, which is your dead time. Here's an example of what I just gave you some background information on. First of all, you have your tau, which occurs around, you start around 63.2% of your input step and go down to right around where it starts to jump up. And your dead time T0 is the few seconds that it takes to start stepping up. And your gain is the difference in your output over your difference in your input. And here's an example of the FOPDT step-up model. You have your model input percentage right here, and your step occurs right here around 10 seconds. You have your, and that's around 65%, and it steps up to 75%. You have your model output, and it's around 22 pounds per minute, and steps up to 27 pounds per minute, right around 10 seconds. And here's the experimental output, and it lines up pretty well with that. And based on the model parameters, you can figure out your gain and your dead time and all that stuff for for your system output. Here's our results from our step up and step down experiments for the low, mid, and upper ranges. This is your visual gain, which is the actual experimental gain. For the low, at the step up is around 0.495 pounds per minute per percent, and the FOPDT parameter set is around 51.5, so that gives you maybe a 1 or 2% difference, which is pretty close. So it shows that the modeling parameters help you out pretty well. And here's the dead time. The red is the experimental dead time, and the blue is the FOPDT model dead time from the parameters that you model. And as you can, this shows that they're pretty close all the way through for each range. So that shows that the FOPDT model is pretty accurate. And here's the time constant parameters for each of the ranges. The green is also the experimental, and the blue is the FOPDT model. For the frequency response, I'll go ahead and show you an example of one of our experiments. This is a baseline of 81%, which gives you an output of about 26 to 33 pounds per minute. You can find your period from TU, which is the difference in the two ways up at the top, and then find your ultimate frequency from that. And in this example, the ultimate frequency is 0.3 hertz, and the amplitude is 7%. Here's one of our buddy plots from our system. Shown here is ultimate frequency of 0.53 hertz, which occurs at a phase angle of 180 degrees, and an amplitude ratio of, I believe, around 0.4 pounds per minute per percent. Here's a model of our amplitude ratio compared to the actual experimental model, and I'll show you some results from that here in a minute. This is the model gained by manipulating the T-naught. It's pretty close. Our model gain for the low was around 0.65 pounds per minute per percent. The mid was around 0.69, and the high was around 0.45. Our dead time showed to be about 0.75 for the low, 0.6 for the medium, and 0.5 for the high. The response time was 0.65 for the low, 0.52 for the mid, and 0.4 for the high. And our ultimate frequencies for each were around 0.45 for the low, 0.5 for the medium, and 0.65 for the high. Our ultimate gains occurred at 3 pounds per minute per percent for low, around 2.3 for the medium, and 5 for the high. This is our order, which is around 1.4 for all three. And this is an example of a comparison of the model to our using our FOPDT parameters and one of our experiments. From this, we got a frequency of 0.05 hertz. And now I'm going to tell you a little bit about the root locus plots, which help you determine different gains for a system and tells you what the system characteristics are going to be like, whether it's going to be underbent or overbent. Down here at this range, when it levels out, is your critically dent gain, and that's where your zeta equals, or your decay ratio equals 0. And as you go up, your decay ratio goes closer to 1, and when you get to your ultimate gain, your system becomes oscillatory, and your decay ratio equals 1. And for this, you want your gain somewhere in this area, and that'll get your system pretty leveled out with not too much oscillation. Won't have too long of a settling time, and it also will not have too much offset. Down here, your offset gets pretty big, but up here, like I said, your oscillations become large. Here's an example of the root locus plot for the low range. As I said,